Okay, so in this video, we're going to look at the third theorem, third theorem of Laplace, which in my opinion is the hardest. It's the most difficult theorem because it's very unintuitive to derive from first principles. In fact, the way that I'm going to do it, I'm not going to do that. I don't know how to do that. So I'm just going to start with the theorem, and I'm going to show how it's true. But it's not like the other two where you can easily just derive it. So that's the first thing. I think what I'm going to do to start with this theorem is just by opening with a question of kind of what we're going to be trying to do. So if the question stated something like this: what's the Laplace transform of sine 2t on t? That'd be like the kind of question here that we're dealing with. It's what happens when the function, we're trying to work out what the Laplace transform is of a function divided by t. So here's the theorem. The third theorem states the following, that if we have, the Laplace transform of f of t equals f of s, then we can say that the Laplace transform of f of t divided by t equals the integral between positive infinity and sigma equals s. So we're using a substitution here of f of sigma d sigma. And the other problem with this, or the other issue with this theorem as well, the added complexity in addition to the substitution of the integration, is that we can only do this if a real limit exists for f of t on t. If we have something like 0 divided by 0, then we don't really know if the limit exists or it doesn't exist. So for that, we need to use L'Hopital's rule, which we're going to go through as well, hopefully in an example. So what I'm going to try and do now is prove that this theorem is true, starting from the right side, going to the left side. So let's do that over here. So we can say, first of all, let's evaluate what f sigma is. That's the first thing to do. So I'm just going to write down exactly what we've done here, the integral between infinity and sigma equals s of f of sigma. I'll do that in a different color to make it a bit clearer. So f of sigma is just going to be the semi-infinite integral between infinity and 0 of the function itself, let's say of f of t, e to the minus, normally we'd say e to the minus st, right, because f of s is assuming that it's e to the minus st. Because we have a sigma here, it's going to be e to the minus st. Sorry, e to the minus sigma t. Yeah? E to the minus sigma t d sigma. And that's what f sigma really represents. Everything over here. Sorry, that's not going to be d sigma, that's going to be dt. This is going to be d sigma. Over here. So let me just write that out again to make it a little bit clearer. So it's going to be the integral between infinity and sigma equals s. That's the same thing. Of f of sigma, well, f of sigma is just going to be the normal valuation, f of t, e to the minus sigma t, dt. d sigma. Okay? Now that we've got this, what we can do is play around with the integration. So we can take out the integral over here and place that on the outside, and then place this integral on the inside, and we can see what we can get from that. So let's come down over here. See that? This is why this is a little bit tricky, this one. So I'm just going to take out the inner one to the outer one. Got in between infinity and 0. and then I'm going to take out, and I'm just going to swap them round. So we've got another integral between infinity and sigma equals s of f of t e to the minus sigma t dt d sigma. Now what I'm going to do is take this function and place it over here. So we end up with infinity and 0, f of t, and then again infinity and sigma equals s of e to the minus sigma t dt and d sigma. And then what I'm going to do is just swap these two round over here. I'm going to rewrite this again. So now we have between infinity and 0 f of t between infinity and sigma equals s of e to the minus sigma t d sigma dt. Okay. Now that we're at this stage over here, what we can do is try to evaluate this integrand over here between infinity and sigma equals s, e to the minus sigma t d sigma. Does that look something that could be possible? So it could be. Let's have a look. So if we take just this part over here, back up to here, let's try and evaluate that. So we're evaluating between infinity and sigma equals s, e to the minus sigma t d sigma. So that's just should be a fairly normal integration. So that wouldn't that be minus 1 on t e to the minus sigma t evaluated between the positive infinity and sigma equals s. Yeah, you can see that there. So let's carry on with this. Minus 1 on t e to the minus infinity is going to be 0 minus e to the minus st. Yeah. So that leaves us with e to the minus st on t, which is basically everything in this red bracket over here, which we evaluated. So if we substitute that back into here, we should end up with the following. So I'm just taking what we have over here, the integrand of positive infinity between positive infinity and 0 of f of t, and now I'm going to sub in this e to the minus st on t dt. Okay, now this should look familiar, because what we have now is, just to state the obvious, the integrand between, evaluated between infinity, positive infinity and 0 of f of t, e to the minus st dt, all on t. I.e., this is really the Laplace transform of f of t on t. Yep, because that's exactly what we have over here. That was just to write it out, just to be a little bit clearer what that really is. Let me just bring the paper down a bit. What that really is now, so we've got between positive infinity and 0 of f of t e to the minus st all on t dt. and we can see that that is the Laplace transform of f of t on t. Yeah, f of t on t. To make it even clearer, we could write it like this, f of t on t, e to the minus st dt. And now you can clearly see that this really is the Laplace transform of f of t on t. Okay, the integral between infinity and 0 of f of t on t, e to the minus st dt. Therefore, we can say what we said above must be true. That the Laplace transform of f of t on t really is the integral between positive infinity and the substitution of sigma equals s of f of sigma d sigma. So I know this was a little bit more convoluted, no pun intended. But it really was quite a tricky one to actually to show this. But the point is that it works, and we've shown that it works algebraically. And now what I'd like to do is try and actually use this in an example to show how it works in practice. When you're using this in practice, it's actually a lot easier than going through all of this. It really is a lot more simple to it than doing this. Okay, so let's have a look at trying to find the Laplace transform of sine AT on t. See that there? Sine AT on t. Not referring to the American mobile phone company, for those of you that understand that, AT&T. But anyway, never mind. Stupid joke. Right. So how are we going to go about doing this? So the first thing is when we, again, see the function on t, let's write out the theorem. So the Laplace transform of f of t on t equals, between positive infinity and sigma equals s of f of sigma d sigma. So first of all, let's have a look at what the Laplace transform of sine AT is, which we should know by now is a on s squared plus a squared. So that's fine. The only problem is that we need to test the limit to make sure that one actually exists of f of t on t. So what we're trying to do, what we need to do first, is see if there's a limit that exists as t tends to 0 for f of t, which in this case is sine AT, on t. Which equals, well, as t tends to 0, sine AT is going to tend to 0, and t is going to tend to 0. 0 divided by 0. So what is 0 divided by 0? 0 divided by 0 could be what? I'm trying to think. That's quite a philosophical question. 0 divided by 0. Well, it's really impossible to know. And I'll leave it to you to think about why it's impossible to know. So we'll put a big question mark there. So in other words, we don't actually know if there's a limit that actually exists. If you have 0 divided by 0, that's undefined behavior. So what we need to do is use something called L'Hopital's rule. L'Hopital's rule. I'll put that in red to find out if a limit actually exists. So we can say, just underneath here, using L'Hopital's rule, what we do is that we differentiate the numerator and we differentiate the denominator, and then we test the limit for t as t tends to 0. And if a limit does exist, then we can assume that there's a limit that exists in the regular case of f of t on t. So what we'll do is that the derivative of sine AT is going to be a cos AT on 1. Yep. And we want to test the limit as t tends to 0 for this function. And that's going to be, well, cos 0 is going to be 1. That's going to be a on 1. It's going to be a. And that implies that a limit does exist. Okay? And therefore, if the limit exists, the third theorem can actually be applied. If the limit does not exist, then we cannot apply this third theorem here. So that's all good. we've got the Laplace transform of f of t, sine et, a on s squared plus a squared. So how do we use this rule with this example here? So it's very, very straightforward. I wish we could see that. So all we do is we do the following. We say that the Laplace transform of sine at on t equals, so I'm just taking it from here now, the integral between positive infinity and sigma equals s of f of s. Well, sorry, f of sigma. Well, we know what f of s looks like. F of s just looks like this, isn't it? Because that is f of s, yeah? Assuming that f of t is sine at. So f of sigma is just going to be this thing over here, right? But with the s replaced with sigma. So that's going to equal, f of sigma is going to be a on sigma squared plus a squared d sigma. Yeah? And this is actually a little bit of a tricky integration here because that is actually the inverse tan. That is the arcus tan function. That'd be the arctan sigma on a, I believe. I think that's right. If you differentiate the inverse tan function of sigma on a, then you'll end up with this. And we need to evaluate that at those limits, at positive infinity, and when sigma equals s. So if we continue, you can see that there, yeah, we can say that it's going to be the arctan infinity on a. We know what the inverse tan infinity looks like. That's going to be as the angle tends towards 90 degrees. So we can say it's going to be pi on 2 minus the arctan of s on a, yeah, because we're evaluating it between when sigma equals s, yeah. And if we actually draw out a little triangle here, let's say we have two angles, alpha. Well, let's do alpha first. Well, no, let's do alpha and beta. And let's put a there and s over here. We can say that the opposite and adjacent, we can say that the since alpha equals the arcus tangent of a on s, and we can say that the beta, and we can say that the beta angle here is going to be again the opposite over adjacent, s on a. So the beta is going to equal arcus tangent s on a, yeah? And we can see that alpha plus beta have to equal 90 degrees, pi on 2. So we can say, therefore, that since alpha plus beta equals pi on 2, we can say that the arctan of a on s plus the arctan of s on a must equal pi on 2. Yeah? And if we look up here, we've got pi on 2 minus arctan s on a. Well, pi on 2 minus arctan s on a is going to be equal to the arctan a on s, isn't it? Yeah? You see that? If I just rewrite that, pi on 2, we take this to the other side, minus arctan s on a. Okay, and we're left with the left-hand side arctan a on s. Yeah? So therefore, we can say that this, going back up to here, we can say that that thing over here must equal the arctan of a on s. Therefore, we can say that the Laplace transform of sine at on t equals the arcus tangent of a on s. Okay? Okay, so let's have a look at another one. We've got the Laplace transform of 1 minus cos 2t on t. So the nice thing about using the third theorem is it's very, very easy to identify. If you've got the function divided by t, you're using the third theorem. So let's write out the third theorem at the top in small so that we've got it. Laplace transform of f of t on t equals integral between infinity and sigma equals s of f of sigma d sigma. Now, the first thing, again, we need to do is check that the limit exists as t tends to 0 for the function on t. So let's do that first. So let's look at the limit as t tends to 0 for 1 minus cos 2t on t. So that's going to equal 1 minus 1, which is 0, on 0 equals 0 on 0, which is undefined. Which means that we don't know if we can use it or not. So let's use L'Hopital's rule to find out if the limit exists. So what we need to do is differentiate the top and the bottom and find the limits t tends to 0 and see if there's a defined solution. So we're looking at the limit as t tends to 0 for the derivative of the numerator here, which is going to be, what's that going to be, 2 sine 2t on 1. Which equals 0 divided by 1, if I'm not mistaken. And that we know definitely equals 0. Therefore, we can say that the limit does exist. And therefore, we can use the third theorem over here. So let's go ahead with that. The Laplace transform of 1 minus cos 2t equals the Laplace transform of 1 minus the Laplace transform of cos 2t by the principle of linearity, which we've covered before. And that is going to equal, that's going to be 1 on s minus s on s squared plus 2 squared, which is 4. Yeah? So now we know what the Laplace transform of f of t is, which is the top part. And the question now that we have to look at is where do we go from here? So let's proceed as we did before. We can now say that the Laplace transform of 1 minus cos 2t on t equals, I'm just taking the definition over here, in positive infinity and sigma equals s of f of sigma. Well, we know that this equals f of s, this thing over here, yeah, covered before. So we just replace that, and instead of putting the s, we're going to put a sigma. 1 on sigma minus sigma on sigma squared plus 4. Yeah? And that's going to be d sigma. So we can actually proceed directly with that integration as follows. So you can say 1 on sigma, that's going to be ln sigma minus, what's this one's going to be? This is going to be, well, ln of sigma squared plus 4. If we differentiate that, that's going to go to 2. So this is going to be half. Yeah, it should be half ln sigma squared plus 4. Yeah? I think that's correct. And that's going to be evaluated between positive infinity and sigma equals s. Yeah? And say ln sigma minus ln sigma squared plus 4 all to the power of a half. And then that's going to be simplified even further to say ln sigma on sigma squared plus 4 rooted. Yeah? And that's going to be evaluated between positive infinity and sigma equals s. So okay, so over here, we need to think about this a little bit carefully. How we're going to evaluate these limits here. So what we could do is just write out what the expression is as ln of infinity on infinity squared plus 4, all rooted, minus ln of s on s squared plus 4, all rooted. Now, as you can see here, infinity squared plus 4 is just going to tend to, is really an expression of infinity, isn't it? Because you can't add 4 to infinity. And root of infinity would be infinity, and infinity on infinity would be 1. So this is actually going to tend towards ln 1, which is 0, minus ln s on s squared plus 4. That was a bit tricky. So this is actually going to equal ln of the square root of s squared plus 4 on s. Yeah, because I'm taking the negative reciprocal here. So we end up with ln of root s squared plus 4 on s. To simplify this a little bit, what we could do is just square the top and the bottom, the numerator and the denominator. And then say the following: ln of sigma squared plus 4 all on s squared rooted. So what we wouldn't do is not square the numerator and denominator, but we could take the square root of the whole thing and then just add another square to the bottom, because that's effectively the same thing. Square root of s is s squared is s, and the square root of sigma squared plus 4 is the root of sigma squared plus 4 on the root of s squared. So that would be the final answer to the Laplace transform of 1 minus cos 2t on t. Quite a tricky question. Quite a tricky question.